Hello, my name is Kendall Hendrix. I'm a chemistry PhD student. My research project is about the effect of pyrolysis heating rates on precursor-derived silicon oxycarbide ceramics. Silicon oxycarbide ceramics have a unique set of properties, namely high creep, chemical, and thermal resistances, and have been studied as a material for a wide variety of uses, such as those listed here. They have two main chemical regions, a glassy domain of silicon atoms coordinated to oxygen and carbon atoms, and a graphitic carbon phase referred to as free carbon. These ceramics are formed through pyrolysis, which is heating the precursor to temperatures at or above 600 degrees C. Traditional pyrolysis in a tube furnace can prepare many grams of sample at once, but it's slow on the order of several hours. Ultra-fast techniques like laser pyrolysis only take a fraction of a second, but only a sample the size of the cross-sectional area of the laser beam is pyrolyzed. A new technique has been developed which can pyrolyze up to a gram scale of sample within a matter of seconds. We propose that not only is this pyrolysis technique more time convenient, but it will also produce a material with a detectable difference in structure. Samples were created through a sol gel process. Two recipes were used. The first with methyl triethoxysilane, here referred to as NTES, and the second with bis triethoxysilomethane and triethoxysilane, here referred to as BTEM. The chemistry of both recipes is the same. The starting materials are hydrolyzed, converting the ethoxy groups to hydroxy groups, and the hydrolyzed molecules undergo condensation to produce a cross-linked network of silicon, oxygen, carbon, and hydrogen atoms. These newly synthesized green samples are pyrolyzed to 1100 degrees C in argon using two techniques. The standard pyrolysis technique in a tube furnace with a heating rate of 2 degrees C per minute, as seen on the left, and the new fast pyrolysis technique with a heating rate of about 3000 degrees C per minute, as seen on the right. This fast pyrolysis technique works by passing a high current through a graphite felt that has a pocket cut into it to hold the sample. The first characterization technique we used was Fourier transform infrared spectroscopy. The starting green material is seen in the blue curve, the fast pyrolyzed sample is seen in the orange curve, and the standard pyrolyzed sample is seen in the gray curve. Here, we don't see much of a difference between the two pyrolysis techniques. The orange and gray curves are similar to one another and both clearly distinct from the blue curves, suggesting that the same general transition from green body to ceramic occurred during both pyrolysis techniques. We next turn to thermogravimetric analysis to see if the weight loss events change during fast and slow pyrolysis. Of course, our 2GA is not capable of pyrolyzing at a rate of 3000 degrees C per minute, but we could compare our 2 degrees C per minute to a very fast 50 degrees C per minute, which only takes 20 minutes. Here we see the same 2 weight loss events for NTES and the same 3 weight loss events for BTEM, with the faster rate slightly shifted to the right, which is to be expected. There was no significant difference between the final weight losses, being within about 1 percentage point of each other. The real differences came when we analyzed the materials with solid-state silicon nuclear magnetic resonance spectroscopy. This type of NMR tells us about the coordination environment of the silicon atoms. Each peak corresponds to a certain number of oxygen atoms coordinated to each silicon, with higher coordination on the right. Here, we see a significant difference between fast and standard pyrolysis techniques. In both of our systems, each silicon starts tri-coordinated with oxygen. At high temperatures, the silicons undergo redistribution reactions, creating quad, di, and mono-coordinated silicons where they didn't exist before. The fast pyrolyzed samples have a much higher amount of tri-coordinated silicon and a lower combined amount of quad, di, and mono-coordinated silicon. So we were able to successfully produce SiCO ceramic material using a new fast pyrolysis technique, which drops pyrolysis time by 4 orders of magnitude while still allowing production of relatively large amounts of sample. We showed that high temperature redistribution reactions were suppressed during the fast pyrolysis. That pyrolysis heating rate can be used as a tool to modify silicon coordination in SiCO ceramics. Thank you so much for listening to my presentation, and I hope you have a great day.